Welcome to LIB Academy once again. In this video, I'm going to take you through Thorium Decay series, one of the decay series that actinide series undergoes. Actinide elements undergoes. This is just a standard thing that you should know. By the end of this video, I'll show you a way of just not memorizing each individual nucleides in the process, but you'll be able to write the result without memorizing the individual nucleides. So to begin with this video, this decay series is going to involve the emission of alpha and beta particles, and we have to know the effect of alpha and beta particles on a nuclide. For alpha particle, we have alpha particle with a mass of 4, and then proton number of 2. And this is also a beta particle with -1 and 0. So for this, assuming if we have an element A with atomic number of 24, and then with a mass number of 24 and atomic number of 2, let's say 5, undergoing an alpha decay. At the end of the day, we are going to get alpha particle here. And how do we know the nuclide involved? The nuclide involved, we know that we are going to produce alpha particle. So the principle is that the total masses at product sites will be the same as total masses at reactant site. Same will happen to atomic numbers or proton numbers. So we have a mass of 4 here. What mass are we going to add to 4 to get 24? So it's definitely going to be 20, right? So for the proton number, we have 2 here. What mass are we going to add to get 5? Definitely going to be 3. So when we are done, just based on the proton number or the atomic number to look out for the element here. For the element involved. So you know that atomic number 3, you compare to the periodic table to see what element has an atomic number of 3. So it's going to be lithium, right? So the same happen to beta decay. If this will undergo beta decay, it means at the end of the day, we are going to get beta particles at our product side plus a certain number of something. Now using the mass problem and the atomic number problem, what mass can we add to 0 to get 24? So it's just 24. And for the atomic number, what mass can we add to -1 to get 5? It's going to be 6. So what element is atomic number 6? Carbon, right? So this is the effect of beta and carbon, beta and alpha particles on a nuclide. If the nuclide to emit one of any of them. So we are going to use this principle to fill out the spaces here. And so we know that looking at thorium, the thorium decay series starts from thorium-232. So just know that. So thorium-232, and we have 232 and here 228, means that we have a decrease in mass by 4. This is going to be an alpha decay. Decrease in mass and also a decrease in atomic number by 2, giving us 88. It's an alpha decay. Once you see the decrease in mass by 4, just know that it's alpha decay generally. So for this one too, from 228 to 228, but an increase in atomic number. You could see that when we're doing the beta decay, the initial atomic number is not the same as the atomic number of the element that we produce in the coda. It increased by 1. So looking at this is a beta decay, and 228, and increase in proton number, which is beta decay, and 224, decrease in mass by 4. This is an alpha decay. And here we have 224 and 220. This is also an alpha decay. We have 220 and 216. This is an alpha decay. We have 216 and 212. 216 and 212, decrease in mass by 4, which is an alpha decay. So we have 212 and 212, but an increase in proton number by 1. This is a beta decay. So we have 212 and 212 here, increase in proton number by 4 from 83 to 84. This is also a beta decay. And we have 212 to 208. This is an alpha decay. So how many alphas do we have in this process? So 1, 2, 3, 4, 5, 6 alphas. So we have 6 alphas. How many betas? 1, 2, 3, 4 plus 4 betas. So This will tell us that, and how many steps do we have here? To know the total number of steps, we just count the total number of hours involved in the process. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 steps. So 10 steps for thorium decay series. So now that we know the total number of alpha particles and beta particles involved, we can write our our net reaction. So starting from thorium-232, we have thorium-232, 232, giving us a last stable nuclide, which is, a stable nuclide at the end, which is lead 208, lead 208, giving us 6 plus 6 alpha particles, 6 alpha particles, and plus 4 beta particles, 4 beta particles. So this is the net reaction for this, for thorium decay series. So the net reaction for thorium decay series is just this. So now, what exactly is decay series about? Is about, for decay series, we have a radioactive nuclide, which means it's not stable. And because it's not stable, as time goes on, it will emit a particle to, and decay to another nuclide. And that nuclide, to when it is not stable, it also decay, emitting particle to another nuclide. And this will continue till a stable nuclide is obtained. So for the three decay series of the actinide element, they mostly end at lead. They mostly end at lead isotope. Now that we are done with the net the net equation, let's look at why is this reaction 4N series. Mind you, thorium decay series is 4N. It's a 4N series. So I have a chart here. You just take any of the mass in the product, either in the product or the reactant. This one right here, either 232 or 208, and divide it by 4. When you divide it by 4, we can do it here. 232, which is mass of thorium here, over 4, or 208 over 4, 208 over 4. If you get exactly a whole number, then it is a 4N series. If you get a whole number and if you get a decimal value and it is 0.25, then it is 4N plus 1 series. 0.5 is 4N plus 2 series, and 0.75 is 4N plus 3 series. So looking at this, if we divide, I decide to take 234. If we divide 234 by 4, it's going to give us 23 by 4 here is going to give us exactly 58. So which is a whole number. Therefore, this decay series is a 4N decay series. So that's it. And the last thing we want to do is I want to give you a shortcut of not memorizing the individual nuclei. So as far as we know the number of particles involved in order, then we'll be able to write the product, to draw the decay series or write the decay series from beginning to end without the need of memorizing the nuclei. So we know that we have alpha, beta. Let me just write it here. We have alpha, beta, beta, 4 of the alphas, and then beta, beta, alpha. So just memorizing this, you'll be able to write the thorium decay series. So you know that this is alpha, beta, beta, and here it means alpha repeated itself 4 times, and we have beta, beta 4 in order, right? So let's say I'm to draw this, to write this decay series, and I don't know where, like, I don't know the individual nuclide involved, but I just know the beginning, which is very important. You also have to know the starting point and this. With the starting point and this, we are okay. And you should know that. So if I should start with thorium, I know I start with thorium 232 90. So first of all, I know it will undergo alpha decay. When you undergo alpha decay, we are going to get a deduction in mass number by 4, which will give me 28 and 228, and atomic number, there will be a reduction of 2, which will give me 88. Then I'll just stand on this 88 to compare to the periodic table and see the element with atomic number 88. And this is going to give me radium. You get it? So now I know that after alpha decay is beta decay. So this will undergo a beta decay. So beta decay means mass number will be the same. So 228, and atomic number here is going to increase by 1. So 8 plus 1, which is 9, right? So then I'll therefore stand on this, look at the element with the atomic number 89. Then I'll write it here. It's definitely going to be action, right? So you continue this process up to the extent, up to the point that all your particles are done. Then you know that, oh, that is where you have to stop. So with this and the starting material for thorium decay series, which is thorium-232, you'll be able to write the decay series. So thank you for watching. So what about neptunium um, series? We have 3 of the decay series. What we should get 4, right? We should be dealing with 4. I mean, why is neptunium not part? So Neptunian series is no longer considered as a significant decay series on Earth due to its short half-lives of its members. So that is why Neptunium series is no longer considered significant. So thank you once again for watching, and don't forget to check other videos out.